Okay, let's look at another basic property of the tensor product. The tensor product is commutative in the following sense. If you have modules m and n, or if you like, think of vector spaces m and n, and you look at the tensor product m tensor n, then this is the same, and by the same I mean isomorphic to the tensor product n tensor m. And this is the sense in which the tensor product commutes. And the proof is rather easy, but it's a nice exercise using the universal property of the tensor product, which is why I'm going to show you how to do it. Just as a reminder, I have here a diagram that is supposed to remind you of the universal property of the tensor product. So let me walk you through this again. So suppose we have the Cartesian product of m and n. Remember, this is basically a set that consists of pairs mn, and we have and suppose we have a bilinear map, which is abbreviated here by bil. So we have this map bil from m cross n to p, and p is of course another module or another vector space, depending on your preferences. And then the universal property of the tensor product said the following. First of all, you can project this space n cross n onto the tensor product by a projection map, which I will call pi. And then from this tensor product, which as you all also remember is just another module, there is exactly one map, and this map is linear. I should mention this again. This map is linear. There's exactly one linear map such that this diagram commutes, meaning you can either walk this way using this map bil, or you can go pi and then follow this by this uniquely defined linear map, and you get the same. So this is what the universal property of the tensor product was, and now we're going to use this to prove this statement here, that m tensor n is isomorphic to n tensor m. And our plan is the following. We are going to show this on a generating set for m or n tensor n or n tensor m respectively. And since these modules are generated, of course, by the generating sets, if we show this on the generating sets, we will have shown this on these modules. So let's, you will see what I mean better by the time I'm doing it actually than me trying to explain it in advance. So let's start. So this is now the proof. So let's start with a map from m cross n to n tensor m. So we have switched the order here from mn to nm, and this is a map that does the following. It sends pairs of this form mn to n tensor m. And by the way, the tensor product is defined. This is of course a bilinear map. So this is bilinear. So we could call could again call this Bill, but since we are going to have another bilinear map in a moment, let's just call it phi. And let's remember that phi is a bilinear map from this Cartesian product to this module n tensor m. And now we are, of course, going to use the universal property, meaning we can project onto the tensor product n tensor n, and then we have a unique linear map. Let's call this one phi bar. So we have and this one pi 1, if you will. So we have a unique phi bar that such that phi is the same as this projection pi 1 followed by phi bar. So this means that if you want to write it down all the elements, this means that m comma n gets mapped to m tensor n, and this gets mapped to, again, gets mapped to this element n tensor m. And now we do the same diagram for n cross m. So we have n cross m, the Cartesian product of n with m, and we write down a map which is again bilinear, which is analogous to this map phi. Let's call it psi. We have a bilinear map psi from n cross m to this tensor product. And of course this sends a pair n comma n to m tensor n, but look, I don't have to write it again because we already have this element here, so this gets mapped to this element. And again, by the universal property, we can also look at the projection to the tensor product, which we already have over here, so which is convenient. So we can use this projection. Let's call this pi 2. And then we know that we have a unique map. Let me use another color to make this more readable. So so we have this, and then we can follow this by this unique linear map from n tensor m to m tensor n, which sends this element n tensor m to m tensor n. And now look, what we have accomplished is we have an isomorphism, because if you let's look at it this way around. If we apply the map phi bar to m tensor n, we arrive at n tensor m, and then applying this new map, which I haven't given a name up to now, so let's call this psi bar, and now following phi bar with psi bar, you see that n tensor m gets again mapped to m tensor n. So this map followed by this map is the identity on these elements that look like these, but these elements generate this tensor product, and the other way around, of course, since everything is completely symmetric. So we see that indeed these maps y bar and psi bar are isomorphisms from n tensor n to n tensor m, and this is exactly what we wanted to prove. Thank you for watching. See you next time.